Naji here. Welcome to my YouTube channel. In this video, we will be discussing on MNIST dataset classification using artificial neural network. So what is MNIST dataset? MNIST dataset is a large handwritten dataset which is commonly used as a dataset for training image classifications. Okay. So this is the sample of dataset. I mean how the dataset will look like. It contains the digit from 0 to 9 and it is written in a different format. We know that. So consider this 0 and this 0 is different, right? So it's a small variations of dataset is there, but it is basically containing the digit from 0 to 9. Our goal is to identify this digit from an image. Okay. So currently we are using ANN, and I'm saying it is ANN, not CNN. We can use CNN also, but in this tutorial we will be only concentrating on the ANN. And each that type of image is a like 28 cross 28 is its size. It's a two-dimensional array. So in ANN is actually expecting a single dimensional array. So first what we need to flatten this one. Okay, so we know that it's a matrix. So in matrix, we need to flatten into 28 cross 28. I mean the 28 cross image or dataset can be flattened. Okay, so when you flatten this, so when we multiply this 28 cross 28, we will get 784. Okay, so the first neuron or first set of neuron in this ANN will be contains 784 neurons. For example, so this is the high level architecture. Okay, this is only for representation. I know like this is not that much good, but this is easy to understand. Okay, so if you look on this input neurons containing like 784 neurons. So how that came? It is came because it has like a 28 cross 28 is its size. Okay, it's a two-dimensional array, so we will expand it or like we will flatten it, we will get 784. Then the second neuron it contains 300, and third hidden layer which is contain 100. So this can be any number of neurons here. So currently for this project we will be using 300. Okay, so when you guys are practicing or when you guys try this in your home or like when you get time, just practice this with like different variations. Like you can try with like 500, 400 like that. Here also you can add more neurons. Okay, maybe like you guys can add more hidden layers and see like the accuracy is increasing by adding more hidden layers, more neurons like that. But for this project we will be using two hidden layers. One is 300 neurons and one is with the 100 neurons. And the last layer or output layer we will be using only 10 neurons. Okay, so why we are using 10 neurons? Because our output expects 10 different digits, right? So here that is why we are using 10. So in these two hidden layers, hidden layer 1 and hidden layer 2, we will be using activation functions as ReLU. Okay, and here we will be the last layer, we will be using the activation function as softmax. So softmax is actually returning the probability of each number. Okay, so in our coming lectures we will be discussing more on activation functions, different activation functions, and all those things, examples that we can discuss. But for the time being, just understand that in these two hidden layers we will be using activation functions as ReLU. In the last layer we will be using the activation functions as a softmax. So here why softmax is because as I just mentioned, like we will be getting the probability value of each number. For example, I am inputting as a digit as 1, right? So after all this processing we will get a result with it's a single array with 10 probabilities. Okay, the probability will be values for 0 to 9. So maybe I input as a 1, right? So it may be like probability of the array list. So maybe let me try to write it here to make it more just a second. Maybe I will add it here. Okay. So the output will be, what I am trying to say, output will be a 10 digit, I mean an array of probability, 10 probability. Okay, so it may be like 0.000, while maybe for the first, for the value of 0 it will be 0.00 probability, and for the 1 it may be like 0.99 may be there. Okay, then rest of the probabilities will be like very less. Okay, so it will be like very less probability, 0.00009 or something like this. Okay, so what we will do, so after getting this output, what we will do, we will select, okay, which one has the maximum probability. Okay, so here we know that even though it has a different probability values, the maximum probability for the one, this position is 0.9, this is the maximum probability, and its position is for 1, right? So we will consider it as the digit, the digit that we have input as a 1. Okay, so that is how the softmax works. Okay, so I believe like it is little confused, but it will be clear when we do this sample code. Okay, so let me remove it and we can start writing the code. So here I will be using Keras. So first we can import few frameworks. We can import Keras, we can import NumPy as NP, and we can import pandas. Okay, I believe everybody is familiar with this NumPy and pandas. Okay, if not, please ensure that you are master in these frameworks, I mean these packages, because this is very essential for a data scientist. I can import Seaborn as SNS. I can use, no need TensorFlow, I believe. Okay, I can import Matplotlib. Here. Okay. Okay, so the Keras is actually providing a data set. Here we can download the MNIST dataset. From keras.datasets, not dataset, it's a datasets. Okay, now we can try to download the dataset. Okay, here we have X-train, here we have Y-train full, and we have a dataset for X-test, and we have a Y-test dataset. We will be downloading the dataset. MNIST.load dataset. MNIST.load dataset. This is actually we are downloading the dataset. It's not load dataset, it is load data. Okay. So downloading is done. Now we can try the shape of, we can print the shape. Okay. Shape of X-train, we can see this one. X-train full. This is the shape. Okay. This is another shape. This is actually value. I can see the shape here. Okay. The shape will be 60K into 28. So it has a shape is actually 28 to 28. Then it containing like 60,000 K images are there. Okay. Now we can see what will be the shape of Y-train. It should be matching. You can see that Y-train full dot shape. Yep. So this is 60, that is the shape. Now we can see what is the value of y train. Y train full. Okay. So its value will be 504, all those things, right? So this is the labels. Now we can plot some values. Okay, maybe I can use IM show. See like X train full. Okay. Now I can say the plt dot show. Okay, so this is the plot function. So we are going to plot the first image from this X train full. Okay. So here this is 5, right? You can visualize this as a 5. Okay. Now what I will do, maybe let me make it CMap as binary to make it, and I can turn it off the axis. I can off it. Okay, something, oh, CMap, it's not CMap. Okay, now this is 5, and we can see that here also the Y train full, the first one is 5. Okay, so these are matching. Now we can try to annotate it. Okay, how it actually will look like. So for that, let me set the fixed size. Okay, this is just for the visualization part. Okay, so whenever we get a data set, like we will do some visualizations. Okay, the SNS is providing a heat map kind of a thing that is very useful to see. Okay, here also I can say that CMap is equal to binary, and I can set I can set the annotation. Okay, so this will give us a representation how it will look like. Okay, so this is how it will look like. Okay, see, so here the rest of the values in this matrix are 0. Okay, and only those areas which has the high values. Okay, that is why it is shown in the black color. It's a dark color here, right? Okay. Now we can come to a few pre-processing steps. Okay, so first what we are going to do, so we are going to normalize this data set. Okay, so for that, since this is a grayscale, we can divide it by 255 to make it normalized between 0 to 1. Okay, so for that, what we can do, I can make it a X train full. This I can be done in different ways, but let me do it simple. I can make it 255. Okay, so before that, let me say that X train full. So let me print the X train full. Okay, it is difficult to see those things. Okay, here we can see the different values, 253, 198 and 0, 156. Okay, all those values will be there. Okay, now what I'm going to do, I'm going to divide it by X train, I'm going to divide it by 255. to normalize this result. Okay. Now it's done. Now let me again print this 0. Now we can see we normalize it to between 0 and 1. Okay, here we can see all the values are coming between 0 and 1. Earlier we are seeing like 80, 150, this all those numbers, but here now it is normalized. So why we are doing this pre-processing step? So normalization always help us to converge the model very easily. Okay. So now we have a test data set is there and we have a full data set is there. Now what we need a validation data set. So I'm going to create a validation data set from the full data set. Okay. So what we will do, I will take x train full divided into 2. Okay, one is for x valid and another is as a x train. Okay. For that, what we are going to do, we are going to select first 500, first 5000 as a validation data set. Okay, and the rest of the values from 5000 to till end. I believe it is 5000. Okay, the 5000 to till end we will consider it as a train. The similar thing we have to do for the y values. So y train. So here what we can do, we can take x train full. We will select it as a 5000, first 5000 as a validation set, and x train full from 5000 to rest we will consider as a training. Okay, so this is done. Now we can see the x valid shape. We can just see what the shape of x valid. So that is 5000, and we can check x train shape. Okay, we can see it as a 55K. Okay, so we are good. Now we need to do, before going to the model creation, what we need to do, one more thing we have to do, we need to normalize our test data also. Okay, so let me normalize it, x test. Okay, so now we are good. Okay, so the next step is we need to create this architecture. Okay, for that Keras is providing a sequential. So here we will be using sequential model. So Keras is provided with a API for that. It's a keras.sequential. Here, as I mentioned, what we need to do first, we need to flatten the data set. Okay, for that, what we can do, Keras dot layers dot, we need to flatten it, right? Flatten. Here we can mention the input shape is equal to 28 cross 28. So this is our input shape. Okay, now we can mention the dense layers. Okay, fully connected layers. Here, as I mentioned, we can, the activation will be ReLU. So maybe let me see here the parameters. We have activation, use bias, kernel. Okay, that's fine. Now we can give one more layers can be added. One is like 100 and activation which is equal to ReLU. Okay. Now our third layer will be 10. Here we will be using a activation of softmax. Okay. Now the model is ready. Now we can see the summary of this one. Model.summary. Okay. So here we can see, okay, this is our model.summary. Okay, so here the first variable is input, because depending upon the batch size, the input size will be vary. That is why it is mentioned as a none. But the shape is 784, and second hidden neuron size is 300, and third is 100, and the last is softmax kind of a thing, that is the 10. Okay, now we can talk about the parameters. Okay, in the first case the parameter is 0 because it is a buffer layer, does not have any kind of activation functions or something like that. It is not a neuron, it's a buffer layer. Okay, in the second case the parameter is 2335 500. Okay, so how that name came is, we can see our neuron is 784 into 300 neurons, right? 784 into 300. Okay, now we have 300 neurons also, 300 bias also. Okay, so this is the extra 300 bias. So when we execute this, we will get 235550. Okay, similar to that, in the second case we will have a 300 neurons will be fully connected with 100 neurons, and each 100 neuron has its own bias. So there will be 100 bias. Okay, so here we can see 3010. Okay, in the last case we can try with the 100 neurons is fully connected with the 10 neurons, and each 10 neurons has its own bias. Okay, so this is 1010. Okay, so this is very clear, right? Now what we can do, we can do a model.combine. So we can use the optimizer as SGD, stochastic gradient descendant will be our optimizer, and we can use a loss function or errors function as sparse categorical cross entropy, and our metrics will be accuracy. So we will be deciding it based on our accuracy. Okay. So we are good here. Now we can start doing the training. Here I can set model dot fit. We can pass X train. We can pass Y train, and we can set the epochs. Maybe I will set it as, make it very less, 10. Okay, so this is also a we can do different options. We can start with less number of epochs and we can try to increase that. Okay, and validation data will be X valid, Y valid. Okay. Now we can do the training. Okay, the training is in progress. We can see that we have set the metrics as accuracy. That is why it is showing the accuracy. So in the first epoch, it has an accuracy of 83 and validation accuracy is 91. Okay, and validation accuracy is 93. This is good. And 95, we can see that it is we can see that loss is reducing and accuracy is increasing and validation accuracy is also increasing. Now it is 95. Okay. So maybe I stop with 5. Okay, let it complete. Anyway, its accuracy is increasing. You can see that. Okay. So the ideal thing is, so normal question is what should be the ideal epoch number. So that is actually a trainable parameters actually. That means like we have to do some kind of a trial and error. So always suggest that you start with minimum epochs, maybe 5 or something like that. If the data set is very huge, okay, giving like 100 epochs and 1000 epochs at the beginning itself will be very difficult. I mean, it may take days to complete. So initially start with maybe 5 or 10 based on your data set size and see like how the accuracy is progressing. Okay, I mean loss is so this variance has to be monitored, and based on that sometimes we may have to do some again we have to do some pre-processing in our input data set, then we need to retrain it again. Okay, so it seems to be almost done. Okay, we'll wait. Okay, now it is done. So we got an accuracy of 96. So try to increase the epochs. Maybe you will get it to up to 98 or maybe 98.5 or something like that. Okay. Now here we can print history. If you see print the history, can print the history. History is not defined. Maybe spelling issues. Let me see. Okay, I'm sorry, my bad. And name it something like this. Okay, so here we can see its loss, its accuracy, and validation loss and the validation accuracy. So what we can do, we can try with a plot. We can see, we can visualize this. Okay, for that I can use pd dot data frame history dot history, and we can plot this. We can see how this works. Let me show this one. Okay, here we can see that blue line is loss. So here we can see that it's a training loss. It is started with high numbers and it is slowly started to decrease. Okay, then it is slowly trying to reach to 0. Okay, then similar to validation loss, start with somewhere here, then it start reducing. Okay, so here we can see our accuracy. This is our accuracy, training accuracy. Training accuracy also start to increase, and it is up to some level it is going to be almost static, right? This is the same with the validation accuracy also. Okay, so from this is the use of the visualization. So visualization is really help us to see like what happens with all those data. Okay, so if you look into the raw numbers, it is very difficult for us, right? Now what we can do the validation part. Okay, now we can do a model evaluation and we can see that how this works. For that we can use our test data. So this is the independent data. Using this we can see how this works. Okay. Good. So we got almost 96% of accuracy with the test data. Now we can try to save this model. Okay. To save the model, what I am going to use is, the OS is saved. So we need to create a unique name. Okay. So for that, let me create. I can create a model name. Make it more specific. Here I am specifying our model path or model directory. I can say it as a trained model. So here I can say that make directory. So if the directory is not there, just create it. Okay, if the model is already existing, then it will not create again. Okay, so that is the meaning of this line. Now I can set a unique model name. Okay, for that I will be using strf time. Here I can mention model as year, month, day. I can mention hour, I can mention minute, and I can mention second underscore dot h5. h5 is the extension of the model that we are going to use. Okay, now we can get the full path. For that we can use os.path.join. Okay, these are the basic Python. Okay, nothing to do with the machine learning. This is just a Python code level that I am using. I am trying to create a model name. That is what we are doing. So I can just print it. The model will be saved in, I can mention full path, and this will be returned. Okay, so maybe I can try to see this is working or not. Get model name to save. Let me see this. Yep, this is working fine. And if you let me refresh here, you can see that trained model. Okay, now this can be saved. This can be saved to a path field. Now I can save the model. I can save the model like keras.models.save model. I can pass model as model. I am passing my model here, and I can pass the file path as path. Let me execute this. So here I can refresh this and expand this. See, our model is saved. Now I will show you how can we load the model. Okay, for that Keras is also providing another method which is called, let's try this, keras.models.load model. See, this load model I can use. I can mention the path, and this can be assigned to a variable, another variable. Maybe I can say it as loaded model. Okay, So this model I can use it for the evaluation also. Model dot eval, we can pass our X train and we can pass our Y train. Evaluate model dot evaluation. I think it's evaluation. I think it's evaluate. Sorry, evaluate. Okay, so the model is working. Oh, sorry, I'm using actually X train and Y train. You have to use X test and Y test. Should be using X test and Y test. Okay, let it complete. Let me run it again, X test and the Y test. Okay, so we got almost the same accuracy. So the goal is how we will save and how we will load this model. Okay, so now let me show you like one more thing. How can we do the prediction part? Once that is done, we can close this tutorial. I think it's being a little long. Okay, so for that, let me assign a variable to result. Okay, here I can do a model dot predict. For the time being, I can select only the 3 from the X test. Okay, so let me take it and let me do the result here. Okay, here we can see this is the a list which contain the probability of each numbers. So as I mentioned, we will be selecting the maximum probability value from this list. Okay, so for that there is a there is a option, that is numpy is providing, that is the argmax we can use, and we can pass the result here. Okay, and let me now print the probability. This is wrong, so I have to mention the axis also. Sorry, forgot. Okay, see, so since we are passing the axis is equal to 1, it is taking only the each array it is taking. Okay, its axis as a 1. So result will be 7, 2 and 1. Okay, so this is the number. So for that, what we can do, we can see like how it will look like. I can take the 0th value. So this is 7, so this is correct. And here I can select y dot test 1. This is 2, which is also correct. And we have a y dot test 2. This is 1. Okay, so this is working fine. And there are like some other features also available, that is callback. There are few callback functions are there, so that we can discuss in our next video, because this is actually become like a long video. Okay, so that is all about in this video. Please do like and subscribe. In our next video, I will show you how can we do like a callback functions, and maybe how can we visualize this kind of a result. Okay, so that's it. Bye bye.